Hi everyone, my name is Taylor Sparks. I'm the editor-in-chief of Integrating Materials and Manufacturing Innovation, and I've got a paper today to talk about that I'm really excited about. It's about mining multimodal fatigue data using reasoning models and a formalized domain knowledge approach. This work comes from two universities. You've got the Fraunhofer Institute for Mechanics and Materials in Freiburg, Germany, and then you've got University of California, Santa Barbara. Lead author here is Jyoti, Prakash, Mohanty. Now, this paper is all about getting data out of the literature and into databases, something that I personally am passionate about. I've seen a lot of work in this area. The exact area where they're working has to do with fatigue data, which is super important because fatigue data is hard to measure. And so it's some of the most valuable data. If somebody has measured it, boy, it would be great to catch that. They point out that not only is it hard to measure, but generating even through high throughput experimentation is probably not realistic. Populating, it says, the high dimensional discontinuous parameter space with high fidelity data is just beyond reach. So we've got to take advantage of the data that's out there. But we all know, if you've been in this field for a while, you know that's hard to do. Trying to mine data from literature is challenging because you're relying on complex reasoning. There are vision involved, right? There is different patterns, there's tables, there's data. People write in different ways. It says here there's varying formats and writing styles. And so in the past, what's happened is that it's relied on a lot of manual annotation or complex labor intensive sort of pipelines for this. But help is on the way. There have been major improvements in language models, vision models, and reasoning language models, right? So our ability should be improving as these different models are improving. They specifically point out the ability to rely on the combination of these things in this paper. So they're going to test a couple things in this paper. First is they're going to explore a couple different architectures, right? Can you just one-shot it? Can you say, here's a structure I want you to follow, go ahead and do it? Can you use existing ontologies? Can you actually use reasoning models? I'll show you how they use those together. And then specifically, the way that they're going to test that is by thinking about extracting data in the same way that humans would do it. Normally, a human would look at a paper, we look at the figures, we identify key labels, legend components, and we try and map that over to what we see in the narrative text. And that continuity between the figure and the text, I think, is going to have additional value from what we've seen in the past when other approaches have been used to just try and take it from the data itself without trying to link it to the additional field descriptions in the, say, the text narrative, right? Let's take a look at their different approaches. They're going to essentially test three different things against each other. The first is this single step approach, right? In this single step approach, this is basically giving the model a schema and saying, do your best to extract everything. This is gonna be our baseline. And honestly, there's a bunch of papers doing this right now. They're still using some useful tools, like they're using Pydantic to force the outcome schema to match something. It should be a good baseline because I've seen papers like this in literature right now. Now, what's gonna be their second approach? The second approach is going to build on this. This is the label-guided approach. Here's where it's looking first at the diagram. It's identifying the curves and the labels in the same way that a human would. It's going to verify those against the text, and then it's going to extract the data once it has those in place, right? This allows us to combine these VLMs and RLM interfaces for the label extraction, validation, and the schema population, as opposed to just accepting a schema ahead of time. But this third approach is where, in my opinion, it gets really interesting, because here's where they're actually validating the outputs against existing ontologies. Here's where we can actually apply logical rules, doing things like run a web search across things and fill in missing test standards that might not have been there. Here's where we can apply things like reasoning models to reconcile things that don't make sense, and this should be actively suppressing hallucinations. What you'd hope to see in a figure like this, where it's showing you on the y-axis is your F1 score, and on the x-axis it's showing you the single step versus label guided versus this more complex label guided and the dynamic knowledge augmentation, is an improvement. If you're going to add all these additional reasoning models and complexity to the model, it should improve your scoring. And what you see is that it does. And one thing I like about this is that they didn't just try this with a single model, right? They've done this with a bunch of different learning models of different sizes to show what types of improvements you can expect to see. The data here came from 60 different publications that they split into 3 different sets, and all that was manually annotated by experts first. And there's quite a bit there, right? They point out that there was actually 206 different fatigue series, and when you take into account the additional information, the target fields for these, that accounts to 6,500 fields, of which a large fraction of those were empty and unknown. So there is a lot here in this paper, and a couple takeaways that I got from it after looking at it is, first off, these field descriptions are critical. They really improve performance. Without them, things really fall off. And that structured output alone really isn't enough. You need to pair it with the domain knowledge and informed definitions. The label guided workflow increases your recall as well, so you get more bang for your buck. You're pulling more of the data out of those papers, and that the dynamic knowledge augmentation is effective at reducing hallucinations, and it is able to fix some inconsistencies. So really, these reasoning models become essential to this process, and the results speak for themselves. With F1 scores between zero point 0.8 and 0.9, we have a really excellent demonstration of the ability to extract materials data from literature. I hope you'll check it out in the latest issue of IMMI.